Okay. Hi, everyone. Thrilled to be here with our 10th event on the Astronomy Untapped Köln. Today, we, including me, Craig,
No.
And Parrot,
Hi.
we are hosting you. And also you see another familiar face here with us today, Veena. She's also part of our committee members, but today she is with us as the presenter of this session. And you also see a new face, Hirishi, thanks to be with us. Hirishi is the winner of this month, but how? Actually, we are posting the Astro quiz every week on Monday on our Instagram and also Facebook page. And Hirishi could answer all the questions in 1 week. It was not only Hirishi, but he was selected among some other, let's say, competitors, and he's invited to be with us. And thanks for accepting our invitation. So can you please tell us a little bit about yourself and what did you get to the Astronomy Untapped Köln?
Yeah, sure. Thanks, Roya, and thanks everyone for inviting me for this talk. A brief introduction about myself. I'm not an astronomer, so I'm the only odd guy in this among everyone. So I'm a backend developer at Reliance Jio. It's a technology firm in India. I develop scalable backend systems based on microservice architecture. I've been interested in astronomy since childhood, and during my undergraduate studies, also I did some astro-related projects. I came to know about AoT from a friend of mine, Alina. She was sharing some of the posts, and I found the posts quite interesting, and the posts have been helping me to stay in touch with my interest in astronomy. So yeah, that's how I found out about AoT, and I've been following their posts, taking their quizzes, and luckily I got an opportunity to be here.
Yeah, sure.
So yeah, I'd request everyone to like follow the page. They have some really interesting posts.
Yeah, thank you. Okay, so our today event is structured like other events as a two-part session. So first we will listen to Veena's presentation, and afterwards Parrot will present us the new thing in the astronomical world. So I will give a short introduction about Veena. Veena is a Humboldt Fellow here in University of Cologne. She is with us from last 2 years. And before that, she was a visiting scholar in Tata Institute of Fundamental Research in India. And she also did her PhD in India in the Institute of Space Science and Technology. Today, Veena is going to talk about the star formation, the perspective from different wavelengths. So we are very thankful that you accepted to present here and present for us. And yeah, floor is yours. Go ahead.
Let me share my screen first.
Yeah, sure.
Hope I am audible enough.
Yeah, that's
Great.
perfect.
Okay, so thank you, Roya, for your kind words. And it's my pleasure to be with you all here today. And in this presentation titled Galactic Star Formation, a Multi-Wavelength Perspective, I will take you all to the world of multi-wavelength astronomy. And being an observational astrophysicist, I will try to explain you why these observations in the different wavelength bands are essential and how we interpret whatever we have obtained through astronomical observations, and with a specific emphasis on star formation in our galaxy, which is my primary area of research. Okay, so let us start with fundamental physics. We all know that the electromagnetic spectrum consists of a wide range of wavelengths and frequencies, apart from the visible light, which we humans are sensitive to. So in the higher frequency or low wavelength range, we have this gamma rays. And in the low wavelength range, we have, in the low high wavelength range, we have this radio waves. And we know that the visible light, as we know, is only a tiny fraction of this electromagnetic spectrum. And also we know that if an object is emitting object is having a particular temperature, then this temperature will have an effect on the electromagnetic radiation. So if this radiation, if the temperature is really high, it will emit mostly in the higher energy or like high frequency side, like gamma rays, which needs like millions of Kelvin. And if the object is, say, for example, at very low temperatures, like a few Kelvins or close to minus 270 centigrade, you can say, then it will emit predominantly in the radio wavelength bands. Now, I will take you back to high school physics, where we have learned this specific law called the Wien's law. So what Wien's law says that the wavelength at which a particular body is emitting, the peak wavelength, is inversely proportional to the temperature of that body. So if the body is at low temperature, you have like high wavelength, and if the body is at high temperature, which means it's low wavelength and high energy side of the electromagnetic spectrum. So this is an example plot, like the curve, which shows the emission of a body at a particular temperature. And here it ranges from, say, 12,000 Kelvin to 3,000 Kelvin. And you can say that like, see that like the visible part is only a very small fraction of this curve, and which is peaking close to, say, like 5,000 to 6,000 Kelvin. So if we consider all the different temperature ranges from millions of Kelvin to few Kelvin, a visible part is like a very tiny fraction of this curve. And regarding this astrophysical aspect, we know that most of these astronomical objects have like a wide coverage of temperatures. For example, on the high temperature side, we have, say, supernova or neutron stars, which have temperatures of order of, say, millions of Kelvin or more. And on the low temperature side, we have some of the very cold objects in the universe, such as like these dark molecular clouds or cosmic microwave background radiation, which is like 2 Kelvin or so. So we know that if we only look at the optical part of the spectrum, we are missing a lot of information. And to get a complete picture of all these objects, definitely we need multi-wavelength observations. So shown here is an image showing like the rough plot of Earth's atmospheric transmittance or opacity. Opacity means that how much the radiation is blocked by the atmosphere. So if the opacity is high percentage, this means that the atmosphere blocks most of the radiation. And if we see the plot, it's evident that in this entire range of the electromagnetic spectrum, we have predominantly, say, 2 to 3 windows. One is the visible one, where the atmosphere is allowing most of the incoming visible light from the outer space to reach the Earth's surface. Then you have like a small window in the infrared. But here still there is like a small level of opacity. Then you have like a part of the radio window, where the atmosphere is completely transparent to the incoming radiation. But apart from that, like the high energy side, for example, the gamma rays, X-rays, and the ultraviolet, they are completely blocked by the upper atmosphere. And this is a blessing to us, because otherwise life would not have existed on Earth. And also the infrared, we see this kind of a variation. This is because most of this incoming light, infrared light, is absorbed by the water vapor molecules in our atmosphere. So we need some observations, observatories that are located at high altitudes to carry out this infrared observations. So if we see the entire spectrum, definitely we need to replace our conventional optical telescopes as we know them, and come up with something that is different. For example, if we look at the high energy part of the spectrum, there are like telescopes such as the Gamma Ray Fermi telescope or the Chandra, the X-ray telescope. These are like mounted on satellites. And in this Gamma Ray telescope, we need like specially designed detectors. For example, here it's like a bismuth germany detector, which can detect the gamma rays. And in the X-ray, you need to replace a conventional optical mirror with that made with ceramic or metal. The infrared telescopes are more or less similar to that of optical, except that they need to be, as I mentioned earlier, either on like high altitude observatories or loaded in aircrafts like the one shown here, the Sophia, or in satellites like the one here, Herschel. And if we go to the longer part of the spectrum, the radio telescopes are completely different from what we discussed so far. It's like a combination of radio receivers and antenna system. So we see that for a multi-wavelength study, we need technologies that are like different kind of technologies, and we need telescopes that using like different technology, which comes in different sizes and different techniques. So I'm not going deep into this techniques as such, and let us move to the astronomical aspect and what results can we see using these different kind of telescopes. So before that, I just want to give you a brief introduction about our astronomical Milky Way galaxy. So most of us know that Milky Way is a spiral galaxy with a lot of spiral lamps, and the location of this is an artistic impression of our Milky Way. And the solar system is roughly located somewhere here. And if we look, since we are like in the within the galaxy, and if we look from like Earth towards the galactic center region, so towards the inner region of the galaxy, if we look like this, instead of seeing a spiral structure, what we will have is more like an edge-on view, right? Because we are looking in a sideways manner. So we will see the bright core of the galactic center and some part of the spiral lamps, etc. And now let us look into like the real pictures or the real data of this view. So shown here is the Milky Way in different wavelength bands obtained from different telescopes. And I have to say that except the optical one, everything else is false colored because our human eyes are not sensitive to the visible light. And if we look at, say, for example, the gamma ray, you can see the bright emission, like the band here, coming from the galactic center. This is roughly the location of the galactic center region. And you can also see some blobs of emission, which corresponds to some of the high energetic sources, such as supernova remnants. And if we move to the X-ray wavelength band, whatever we have seen here as bright is not seen here. Instead, we see some dark patches against some background. So why is it so? Because most of the X-ray radiation is absorbed by the interstellar clouds, which are very cold and dense, and they lie between the Earth and this galactic center. We have like different layers of molecular clouds, and these clouds absorb most of this electromagnetic radiation from like X-ray radiation. So we see these clouds as dark against the bright X-ray background. And if we move to the optical band, the situation is even more worse, right? Like galactic center is almost masked by this interstellar clouds. So let us look to the longer wavelength band, so the infrared. What you can see is, since infrared radiation is not absorbed as much as the optical, we can definitely see some part of the galactic center, like the ones that are blocked by like the interstellar clouds. And apart from that, you can also see the clouds itself in emission. Why is it so? Because the clouds are at low temperatures, which means they emit some kind of some part of like infrared emission. So we see the clouds also in emission, which we see here as bright patches. And in the radio, since radio is like least absorbed by these clouds, you can again see something similar to the gamma ray part and the bright galactic center and all these sources. So I have till now talked about the multi-wavelength view of the Milky Way, but let us now move on to the specific area of star formation. And we know that stars form in the galaxy within dense clouds, and where there are like within these clouds where there are like high density regions, gravitational collapse happen and stars are formed. So shown here is like a 3D simulation of star formation within a giant cloud. And you can clearly see that as time progresses, like in millions of years, there are like inhomogeneities and like filament-like structures are formed, where in these high dense regions, new stars formed here. You can see them as like white dots, but as they evolve, they will start to eject a lot of material through their like polar regions. And these outflows and jets are shown here. And as the star evolves and evolves later at the end stages, it can also have some supernova explosion if star is massive enough. And these explosions can carve out the molecular cloud and create these voids or bubbles within the region. So whatever we have seen like a more smooth cloud now become a complicated region. So this is like a theoretical understanding, but to get a complete picture of the star formation in our galaxy, for example, we definitely need a direct comparison of theory and observation. So we need definitely observational data, but it is not as easy as it sounds. Why? Because the observations of these star forming regions are really challenging. Most of the stars form within like a cold and dark clouds, like the one shown here, which is a active star forming region named as the pillar of creation. And within these dark pillars, there are like multiple stars forming, but it is opaque in optical wavelengths. We are not getting enough information. So the obvious conclusion is definitely to look at other wavelength bands. And I will show here a very simplistic example. This is the image of a cloud, a dark cloud, B68 or Bernard 68. And if you see the optical data, you can clearly see that there is like a dark cloud sitting here. But in the image where there is a combination of optical and infrared. So here again, it's like false colored. The optical image, which is green and red, green and blue, is superposed with an infrared image, which is color coded as red. So if we combine both, we can clearly see that whatever we saw as like a dark patch in the optical, there we see some stars in the background in the infrared data. And apart from that, the cloud itself is now having like a reddish hue. So why is it so? Because this cloud is again at a temperature of say few kelvins, few tens of Kelvin, and there is like some infrared emission from that. And this emission is what we are seeing here as this red nebula or faint nebulosity. And now we will go to the specific star forming region, CH87, which is located roughly 8,000 to 9,000 light years away from the solar system. And shown here is the optical image of this region. And what you can see here is stars and a dark background, like a typical optical image. But if we move to the near infrared band, you are obviously seeing more stars because infrared radiation is like penetrating many of the foreground clouds. And you also see some enhanced like number of stars here and some faint glow or nebulosity and also a dark patch. So this dark patch must mean that this is like a cloud sitting there blocking all the view from behind. And then if we move to the mid-infrared, like say a few microns, which means 10⁻⁶ meter order, what we can see is like a beautiful, beautiful nebula, like an image where you see these two lobes of emission along with many stars. And we keep on looking to the other longer wavelength bands, say again like hundreds of micrometer in the far infrared and submillimeter. And in the far infrared, you again see like the faint part of these lobes. And also the new thing here is whatever we have seen in this image as like dark bridge is now bright like a bridge. And in the submillimeter, it is very evident, this like an elongated structure. And let us now look to the radio wavelength that's say order of 0.4 meter. And it's completely different from what we have seen so far. It's more like a bright blob of emission. So we have all of our multi-wavelength data, and we know that different images, okay, they are showing these specific kind of shapes and emission, but how we interpret them, how we combine them, and what information can we get. For that, let us first look at the individual bands. For example, the near infrared, which is close to say 1 to 2 micron. The emission predominantly comes from dust that is very hot dust, which is having a temperature of typically 1000 Kelvin. Then you can also get an idea about the star cluster if it is present in the region. And you can also identify some of the young stars in this region. And if we go to the mid-infrared, now whatever you can probe is one thing is the warm dust in the region, which is at a temperature of few hundreds of Kelvin. Then you can also identify the hydrocarbon molecules present in the region, and also again the young objects. So you must be thinking like, okay, she's showing some images and saying that you can study this. But how exactly you know that in near infrared is emitting in like thousands of Kelvin, and this other one is few hundreds of Kelvin. So for that, I again bring your attention back to this Bean's law and the black body spectrum. So shown here is a range of emitting temperatures and the corresponding curves. And let us look at the near infrared, which I mentioned. It's like a close to 1 to 2 micron. So, and if we see like the curve corresponding to like 1000 Kelvin, it is peaking roughly at 2 microns. So we know that this particular wavelength, we have something emitting at order of 1000 Kelvin. And if we look at the mid-infrared, which this image is close to like 4 to 8 micron, there the curve is peaking roughly here and with a temperature of few hundreds of Kelvin. So we know that definitely the like different wavelength, they are tracing different temperature dust. The next thing is about the molecules. So if we pass this light from the star forming region through a spectrograph and take out the spectrum, you can see something similar to this. So you will see like a constant emission overlapped with some peaks. And if we compare this with the laboratory spectrum, which means like people have studied the emission from different molecules at different wavelengths, and they have identified like many molecules, like this particular molecule, it will emit at this particular wavelength. So if we compare with that already non-laboratory spectrum with the astrophysical spectrum, you can match the peaks, one-to-one matching of the peaks, and then you can identify like, okay, this particular peak corresponds to this particular molecule. So people have already done this kind of analysis, and they have identified that many of the star forming regions at this particular wavelength, they have emission lines from hydrocarbons, which means that there are a lot of complex molecules, organic molecules, and other species present in such regions. Next thing is about young stars. So whatever you see in these images are just like, apart from the nebulosity, we are seeing a lot of dots, right? Or like stars, point-like objects. So how you know that one dot is a young star and the other dot is like a much evolved star? For that, we use a technique called the color diagram. So if I give a very simple explanation, if we take say one of the star, and you know that like we already have like data at different wavelength. So we take, say, 4 different wavelengths. Here it's like 5.88, 3.6, 4.5. Forget about the wave, like the particular wavelength. But if we take the difference in brightness between one wavelength and the other wavelength and plot it against a third wavelength, difference in brightness between a third wavelength and the fourth wavelength, you can get a plot like this. And in this plot, since the main sequence or like the evolved stars, they don't have any circumstellar dust around them. So they will be not having any excess emission. They will be mostly located close to somewhere here. But for the young stars, apart from their own central, like their own emission, they also have like a lot of circumstellar dust associated with them. And this dust will emit something in infrared, right? We already know that this dust may correspond to like low temperatures, which will have infrared emission. So those objects which are young will also have an additional contribution from infrared. So they will be shifted like this side in the diagram. So whatever that is shifted, we definitely know that they come from young stars. And if we just take the coordinates of these stars and put them in the figures, we know that where exactly in the region young stars are formed. Next, let us move on to the submillimeter band. As I mentioned earlier, we see more elongated emission and we don't see any stars in the image. Why is it so? Because this is at like a very cold temperatures, like 10 to 20 Kelvin, and most of the stars are like really hot and they have negligible emission at this wavelength. So we don't see any components from the stars. And what we really see is dense and cold material, which is like a molecular cloud here in this particular region, which is having like an elongated shape. And similar to the mid-infrared, you can also probe a lot of interstellar molecules using the spectroscopy and, for example, like carbon monoxide, hydrogen cyanide, etc. And in the image, you see some bright emission spots, like we call them like clumps or fragments. And these are the dense regions which may undergo gravitational collapse and form future stars. And finally, at the radio wavelength, what you're seeing is the ionized plasma around O and B type stars. Why only O and B stars? So the reason is that these O and B stars are like the massive stars in the spectrum, and these massive stars are like hot enough in the temperature of say 20,000 to 50,000 Kelvin, so they can emit significant ultraviolet radiation. So the ultraviolet radiation from these massive stars, they will ionize all the hydrogen present in the immediate vicinity, and this hydrogen will undergo like ionization, and from this ionized plasma, this hot gas, it will emit radio emission. So here we are seeing it more like a spherical clump of like bright emission. And we definitely know that in this particular region, there are already some O and B, like one or more stars formed. So we were looking for different clues to get the picture of the star formation activity of this region. And now we have like a different data, like a piece, different pieces of a puzzle. And the next step is to combine all the pieces of this puzzle to get the complete picture. So if we combine all the data and just interpret the result, we interpret all the results, we can get the information such as, first, the temperature and density of the region. For example, we know like this red region, which is mostly emitting in submillimeter, is where the dense and cold cloud is located. And we know that this green emission corresponds to, say, warm dust and also some of the organic molecules. And this white bright emission corresponds to like the regions where newly formed stars are there, and you have like lot of hot dust there because the stars are heating the region. And some other information is like how many stars are formed, and of them, how many are protostars and how many are like more evolved stars. And we can also get of these, which are the massive stars, which are the low mass stars, where are they distributed, etc. And another aspect is you can study the chemical complexity of this region. So what kind of molecules are already formed in the region, and how much how will they evolve, and what kind of molecules they can, like further they can form, etc. And combining everything, we can get a view of the star formation activity, the evolution, and also the age. We can get like, not like an exact age, but it's very difficult, but we can get an approximate age of the star forming region. And we do such analysis for different regions in our galaxy, and we try to do a statistical analysis to see like, okay, how different or how similar are like the properties from region to region, and we try to understand the star formation within the galaxy. So to summarize, observational study of star forming regions are really challenging. And in the optical, we have like very high extinction, and like the clouds absorb all the radiation and we don't get much information. And if we use multi-wavelength bands, we can get idea about objects in different stages of evolution. And if we combine all the data, we get a complete picture of the region. And with advanced facilities and novel observational techniques, new discoveries keep on happening, and we are day by day improving our current understanding of the star formation. So with this, I will stop here. Thank you all for like listening, and I'm happy to take questions.
Awesome. Thank you very much, Veena. I enjoy it. Hope our audience too. You may know that from our last event that we brought this tradition of having a winner of the month among us. We would be happy to start the question session with our guest, but we also are happy to take questions in the chat or in the comments below. So please write your questions, and we will read them, and Veena will kindly answer them. So Hirishi, please, if you have questions.
Yeah, hi. So that's a lot of performance pressure to start the questioning. Anyways, Veena, it was a very nice talk. I like the overall idea of multiwavelength astronomy, where you work like detectives to put up different puzzle pieces together to get a holistic understanding of the whatever object that you are studying. Each piece is like the image from different wavelengths. So my question was, you showed one simulation, right? Where there's a region and yeah, this particular. Can you play it once?
Yeah, sure.
Yeah, so like my question was, if you look at the simulation, initially it's a nearly homogeneous structure, a cloud, and as it evolves, there's fragmentation, and you can see very dense regions forming up. So my question was, what dictates the mass of these dense regions, the cores that are being formed? Like basically, I want to understand that in primordial stars, there's a belief that primordial stars were very massive, but we don't see such stars in the current universe right now. So what dictates the mechanism of fragmentation?
Okay, so to answer that, first I would like to say that the mass of like a clump which will undergo gravitational collapse, that minimum mass is called the Jeans mass, and that Jeans mass is completely dependent on the temperature. And the difference between the current universe and the early universe was that, like in the current universe, you have like the gas comprises mostly of hydrogen, then helium, but also like traces of heavy elements. But in the primordial universe, the cloud was basically most of it was hydrogen, then a little bit of helium, and also like some bismuth, which is like a very low amount. So the metallicity, we call it as like metallicity. The metallicity of the current universe is much higher than that of the early universe. And when there are like a lot of this kind of heavy elements present in the molecular cloud, it acts as an efficient cooling mechanism when the clump undergoes gravitational collapse. So this cooling will make the temperature lower, which means that you will have low Jeans mass, and you can have a gravitational collapse of a smaller clump. But in the early universe, since the cooling was not efficient, the clumps had much higher temperature. So since the Jeans mass depends on the temperature, when temperature is high, the Jeans mass is high, which means you will have like much larger mass fragment, which will undergo collapse and form like more massive stars. And like people have studied and like proposed that the stars in the primordial universe could be massive as like 1,000 times that of sun. But apart from that, one more mechanism which is believed to play a role is the presence of dark matter. In the initial universe, like the dark matter was mixed up with this ordinary matter. So even within the clouds, it was like dark matter is surrounding the normal material like a halo. And it also played a role in like making these primordial stars very massive. But I'm not an expert in the field, so this is what I can answer. Yes.
Yeah, thank you.
Yeah, you're welcome.
Okay, thank you. Are you done, Alicia, or you have more questions?
No, I think I'm done.
Okay.
The
great.
rest of the talk was quite clear.
Okay, thank you. So do we have any question from our audience?
Nothing in the chat yet.
Okay.
So maybe I can ask a question if that's all right.
Yes,
when you're
sure.
looking at, I think it was CH87, when you're looking at it in different bands of light. Sorry, yeah, I guess here is fine. What would it look like in, say, the higher energy wavelength?
Yeah, so this particular region, we don't have any higher energy observations available, but I would say like in the higher energy like maps, you won't see much emission, because one thing is in the gamma ray, to produce gamma ray, you need like very high energetic events, which have like temperatures of few millions of Kelvin, as I mentioned, and these regions are not energetic enough to produce like significant like high energy gamma radiation. And there could be some like a lot of ultraviolet radiation and some X-ray radiation from these regions. But the problem is these are very young regions with a lot of like gas and dust around them, right? So the absorption, interstellar absorption around these clouds will be very high. So they will be blocking most of the high energy radiation. So you won't get much information. So typically, like people like us, we mostly focus on like the longer wavelength part of VM spectrum than the higher energy part. But once these regions are a bit more evolved and some of the gas is dispersed, you can start to see the ultraviolet radiation, for example.
Okay. You mentioned in your explanation dust. What do you mean by dust?
Okay, so the interstellar dust is like a combination of different molecules. For example, silicate molecules, ices, different ices like hydrogen. Then like you have like carbon monoxide ice. Then you have like the nitrogen species. So this is like a whole like a branch of astronomy studying the interstellar dust and like analyzing the properties.
So it's not like the dust that my laptop is collecting right now.
But can you also, now that Craig asked about dust, can you tell us what is specific of them that they make these darkening or they make extinction?
Yeah, so the interstellar dust, the properties that they tend to like scatter most of the radiation from like the nebulae or like stars. So like what you see, like when the sun is like in the horizon, you see sun as like a red than like a yellow, because most of the blue light since it is passing through the dense part of our atmosphere, the dust present in our atmosphere is scattering. So same thing happens in the interstellar clouds also. Like, it's not like only the visible blue light is scattered. If you check like the relative scattering between, say, near infrared and mid infrared, we know that near infrared is more scattered compared to mid infrared. And if we compare between mid infrared and submillimeter, the other one, the former, is more scattered.
Right. Great. I'm sure that Parit has some questions about the smells that one can get from different wavelengths or so. So
Yeah, I was still thinking about a smell or taste question, but the only thing I could think about is whether different kinds of radiation, as we see in this picture right in front of us, taste or smell differently. But I won't ask that because we can't smell or taste radiation. Everybody knows that. But I'm still looking at all of these pictures, and I can't stop thinking about the fact that we can only see in optical, right? So our eyes are able to see some everything in visible light, and but all of these other images also look really stunning and I would say real, but it's a different kind of real, I guess, because since we cannot see infrared light or submillimeter or radio, there has to be some sort of processing involved, right? Could you do you deal with this kind of processing in your work, and can you tell us more about it?
Yeah, sure. So when we take, say, the data from like a specific telescope, like at a particular wavelength band, what you end up with is, after processing, a black and white image like this. And you have such different black and white images at all the different bands. But this image, for example, is an RGB image. So RGB means red, green, and blue. So what we do is, this is only one wavelength band, but this I have mentioned here, say like 3.6 to 8. So this is the combination of 3 images. And what I have done is, I have taken the longest wavelength, the 8 micron, as red. So I have like colored it as red. The middle one, say like at 5 micron, as green, and the shortest wavelength as blue, and combined all the 3. So we get an RGB map like this. So always the rule of thumb is to use the longest wavelength as the red image and shortest as the blue, more or less, and then you get beautiful images like this.
But in the case of the other ones where you don't use an RGB filter, it's probably the colors that we see are added later, right? And astronomers follow the convention that you just mentioned, that okay, we keep red for the longest wavelength and blue for the shortest, right?
Yes, here also see, like in this one I have, since the submillimeter was the longest, I used it as red here. And because there was no other emission in this region, in the other wavelengths, it is very bright red. But in this image, you can see like I have used more than 3. For example, if you see, you are also seeing some magenta contours.
Yeah.
So this is a combination of, say, like 4 images, like RGB. But since I don't have one more like color to overplot, what I did is I just took the intensity contours of the radio image and overlaid this radio image over the color RGB map, just to see the relative distribution between the different bands. So we can use all these kind of like different techniques. We can, again, like if you want like a 5th data to be overplotted, you can plot it in a different contour with a different style or different color, and like combining everything. Yes.
Oh, interesting. Apart from these contours, this makes me think of the time when I first found out, when I had the realization. When I found out that these images are real, but in a different sense, or let's say they aren't that real in the sense of how we use cameras or how we use our eyes. It was pretty pretty weird to find that out, and I was a bit angry at astronomers for not telling me that before. This was in university, I think, and I remember the day I found that out. I was just sitting somewhere, chilling, and reading a space magazine like I always do. And suddenly somebody wrote, "Oh, this is the original picture in black and white, and this is the process picture." And I could not walk with strong legs that day because I was shaking. That's what I remember. I'm not sure if that actually like felt like shaking, but yeah, it is pretty important for us astronomers to see those colors, even if we process them. Do you guys have such an experience? Do you remember the time when you found out that all of this is well, different?
I cannot remember when it was to learn that these are kind of irreal, but kind of opposite side. When I first, for the first time, I made an RGB map of the non-visible wavelengths, I felt like, okay, the only reason I fall in love with astronomy was these fantastic images, and I'm done. Yeah, yes, it was. So I really like them, although it's kind of, yeah, it's not visible to our eyes, I would say.
Yeah, right. I mean, it's not real in the sense that when we look through a telescope, we see exactly the same thing we produce here digitally, but it's still real in the sense that we just have to sort of combine the abilities of what technology we have to produce this image, which is also through filters, and we have the energy information, we have the temperature information. So it's still real in that sense. But yeah, please, who else has experiences, please?
Yeah, maybe our audience can also write it in the comment for us if they have any experience about these RGB images or any experience about observing the astronomical objects, if it has any different with their imagination, with their expectation, how do they feel, and so on.
Yeah.
Okay. Okay, so I take the time for myself also to ask a question.
1 second, sorry, we do have some questions from the audience.
Okay,
that are somewhat related to what Purit was talking about.
Yeah, sure.
So, Tinziose asked, how do you stitch together the multi-wavelength observations? Is there some particular software that you use?
Yes, we have like few of the softwares, and the one I'm using is called DS9, and these astronomical images comes in a particular format called the FITS images with the extension like .jpg, for example. It comes with an extension called .fits, and there are special softwares where it can read the FITS file, and like then you can see them, like process them again, like further in this one. And also you can do this using programming languages like Python. Python has like a completely like a branch for like processing the astronomical data. It's called like AstroPy, and you can use Python codes to combine different images.
And we have another question by Veena. Would there be any benefit to observing gas clouds in shorter wavelengths, like gamma rays? It would be harder to observe.
As I mentioned, mostly these regions are not bright enough in gamma rays, but there are sometimes very high energy events like shocks, or sometimes a molecular cloud when it's like forming stars. It can also like have some supernova explosion, and that can like make this emitting gamma rays. So there are like many mechanisms that can produce like ultraviolet or gamma rays. And I would say most of the time multi-wavelength, the advantage is we may have like a lot of serendipitous discoveries, and like we see something unusual, and if we chase that, we get like a lot of new information. So it's always useful to like look at the different bands. We don't know what is hiding there. It's more like a treasure hunt.
Yeah, that's also Roya. I guess you can ask the question.
Okay. Okay, good. Thank you. So Veena, I'm not sure what was the number of this slide, but where you were talking about these ionized plasma. Yeah, so actually you told us about different things that we can somehow characterize the region we are observing with. So one was the temperature, like paying attention to temperature and connecting with what you nicely explained us in the beginning about these basic things in the high school, the black body radiation. It made me kind of confused that you are talking about the fact that the lower the temperature is, the peak is shifted to the lower wavelengths. Sorry, higher wavelengths. Then how this happened that in the radio regime, we have a temperature, we are observing a plasma with the temperature of above 10,000 Kelvin.
Okay, this is like a really good question, Roya. Like I am glad that you noticed this. So well, you are right. So while we were mentioning about like the other bands, this was mostly based on the Wien's law. Like we are seeing mostly the dust emission from the like this black body or gray body, whatever we call them. But in the radio, since I said these are like meter wavelengths, so the temperature will be like very, very low. And we don't see significant emission from clouds or anything else in this one. But here what we are seeing is not from the like a black body radiation. We are seeing completely different mechanism. So I mentioned that you have like, since the star, the UV radiation from the star ionizes the hydrogen around this, and what you have like is a soup of say electrons and protons, soup of charged particles. And when these charged particles are like moving in the medium, they like deflect when they pass close to each other, they deflect. And when they change their like trajectory, what will happen is they emit some emission, like radiation, and that radiation will be in the radio wavelengths. So this mechanism is called the thermal Bremsstrahlung emission, or in simple terms, free radiation. And it is different from the mechanisms which I discussed earlier.
Ah, okay, thank you. So there are two different mechanisms, and this temperature is it is not something that has been inferred from the black body radiation. Okay, awesome.
And I should also add that the most of the things I listed here are only few of the mechanisms in the regions. But if we look at, say, some other, for example, supernovae, etc., there you have like a synchrotron emission or like Compton scattering. All these terms we like can associate with the high school textbooks, right? So
yes,
many of this play a role in the like the interaction in the interstellar medium, but whatever I have mentioned here are mostly relevant to the star formation studies.
Okay, great. So I'm very pleased with this very nice discussion. If there is no questions or comments, okay. So I thank you again, Veena. It was very nice of you to talk about your research in simple words for us. And let's move forward. I hand over to Parit for the astronomical news.
Thank you, Roya. Please keep your, yes, thank you. Please keep your mics on because I want to hear what you think. 1 second. Yeah. I hope this is visible
Yes.
Yeah?
Yeah.
Okay.
No.
All right. So as always, after all the serious nerd chatter, let's bring you the exciting astro news this past month, or at least what we find exciting. Let's start with some fake news. Because it's also creeping into astronomy these days, so we have to discuss that and take action by telling people what is fake and what is not. Okay, so do you see this picture? And I'm sure you find it really breathtaking. Well, since I started with this, I should tell you that it is fake, but it was popularized as the last image taken by Cassini and received thousands of retweets and likes. Well, by when I mentioned Cassini, of course, this was a mission to Saturn. But let's hear some background from Phil Plait from the blog Bad Astronomer. On September the 15th of 2017, the Cassini spacecraft plunged into Saturn and burnt up after a stunning 13 years of orbiting the ringed wonder. I mean, the way he wrote it actually gives me tears in my eyes. That planet, those moons, those rings, everything Cassini saw and experienced and sent back to us humans on Earth was gasp-worthy and awe-inspiring. Of course it was. We have never seen the like, and it may be decades before we go again. And at the time, many electrons were spilled over the amazement we all felt from the mission. I think he meant tears, but yeah, tears have electrons. And the bittersweet emotions from the spacecraft demise. Also, according to him, the painting is lovely, but there are a few things that give away the fakiness. If you see closely, you don't actually have to see closely. You see it right away. The pressing question one should ask oneself before contributing to thousands of likes and retweets that this image got was why we ask, why would you make the antenna photobomb your view of some important feature on the moon, right? Or in the rings? I mean, this is the worst possible problem that I could have faced. Not the worst possible, but like imagine you sent a spacecraft and by mistake you blocked your view with an antenna. Like it's a lot of waste of a lot of millions of dollars. Also, I don't know if it's really possible to take such a high definition image while plunging into a planet. Like think about it. No matter how good a camera I have, I can't even take a nice picture of a swimming pool when I'm diving into the water. And please stop laughing because I did not try that. But yeah, I mean, you see it and it's fake, right? We don't get such HD pictures from faraway planets right now. But yeah, we will soon. Anyway, moving on a bit closer to the Earth, to our friendly but hellish planetary neighborhood, of course, Venus. Yesterday, NASA was very generous for Venus and finally decided that they are going to return to the up-close exploration of Venus, as they announced two new satellites, Da Vinci Plus, of course, like iPhone Plus. It's better than Da Vinci, which was never launched, and Veritas. Now, Da Vinci is expanded as deep atmosphere of Venus investigations of noble gases, chemistry, and imaging. Someone really forgot how English works. And it will drop a spherical probe of instruments that would sniff and analyze gases as it descends through the atmosphere, right? And the other one, Veritas, or Venus Emissivity Radio Science, INSAR, Topography, and Spectroscopy. Lots of science in this term. Will aim for topographic measurements. The other finalists were also interesting. There were Io Volcanic Observer. So Io is a moon of Jupiter, which is the most volcanically active body in the solar system. And Trident was another mission proposed, which would have sent a spacecraft flying past Triton, the very exciting moon of Neptune. But nobody loves Neptune. Everybody loves Pluto. But now, by the end of the next decade, we might have some really interesting answers to some really exciting questions like what are the concentrations of noble gases like krypton, argon, neon, xenon, and how this might provide hints about the formation of Venus's atmosphere, and also the measurements might find signs of not life, but whether water has escaped from Venus into space, and whether oceans were ever there to cover the surface. Also, whether there is volcanic activity on Venus. And last but not the least, hopefully someone will find some phosphine finally. Sniff it out of the thick clouds, going there and just taking some sample. Please do it. I'm so excited about it. Some people are sad though, because the Trident mission to Triton was supposed to study plumes that could be emitted from the subsurface ocean, of course, because there is some sort of activity that sort of there's plumes coming out to volcanoes. If this hypothesis was true about the plumes, there's no other chance to observe it, because by the time another mission would reach Triton, the moon's activity will have ceased already because of its position in the orbit relative to the sun, etc. There may never be another opportunity to observe these outbursts for 100 more years. That's fine, because I'm interested in going to Venus first anyway, so yeah, this stuff can wait. All right, let's move even closer to Earth and talk about the moon. And for that, we bring you the tweet of the month. Damn you, clouds! I wanted to see the super sunflower celestial orb blood moon total lunar eclipse extravaganza, or whatever it's called. Well, this was weird that stuff happened a few days ago, because this is actually a very accurate description of the moon, but it is also a very accurate description of the frustration we astronomers have with the weather all the time. Even though weather is beautiful and it gives us rain and shine and whatever, but why does it have to come in front of the telescope, right? It's rude. Also, some background. Why am I talking about the moon? This is because in the early hours of May 26th, last month, total lunar eclipse happened, which was also called, well, the blood moon, and was visible from North America. But this trend that I just showed you was a trend. It was not an isolated tweet. Twitter completely took off, and even news blogs promoted this very compact description of the moon that I still can't seem to repeat correctly, because yeah, I mean, you can try yourself. Tonight's super flower blood moon lunar eclipse should be nice for those able to observe it, of course. But next year's hyper ultra happy block party mega sunshine chili cook off. Okay, I'm not going to do this further. But yeah, there were lots of interesting moon names being thrown around, because somebody also had some versions with wolves and other flowers and more flowers. And I guess, Craig, you understand why it's called flower moon in North America. I don't know. Okay.
I have no idea. Sorry.
Okay. Sorry for the regionalism. Yeah, let's move on though. But that's fine, no matter what the name. The moon always stuns all of us. And if you have a doubt, please look at this view of the moon from the International Space Station. This is exactly the same moment, because the moon was a full moon, of course. That's why there was a lunar eclipse, but it was also a blood moon. It's not a very rare occurrence as such, but who will tell me why the moon looks bloody? Short quiz. But it's a short quiz, but the answer has to be long. Any takers? Anybody from the audience, please write down there in the comments. We would love to hear the answers. Please do not Google. There's no fun in Googling. Anyway, let's move on. to even closer to Earth, which is the International Space Station, still not on Earth. Because what's the interesting part about that? Unless you are in the ocean, which is very interesting. Well, the machines had some blood spills this past month because Canadarm2, also known as, well, not also known as, formerly known as the Space Station Remote Manipulator System. Well, I like Canadarm better. Which is designed by the Canadian Space Agency, has been a fixture on the space station for 20 years now. And it's a multi-jointed titanium robotic arm, magnificent, that can assist with maneuvering objects outside the ISS, including cargo shuttles and performing station maintenance. Canada built this one thing and they put it on everything. So on the shuttle, on the ISS, and everybody wants it. Good job, Canada. But it's unclear when the impact occurred, since the damage was first noticed on the 12th of May during a routine inspection. And as you can see here, the object punctured the thermal blanket and damaged the boom beneath. And this is, of course, a sobering reminder again of how dangerous Earth's low orbit is now, because the space junk is sort of a ticking time problem already. There are over 23,000 pieces. Well, there are 23,000 pieces that are just tracked by systems on Earth. But of course, there are thousands and millions of others, smaller pieces that we can't track. Anyway, Craig, our expert on Canada affairs, is personally offended because, like, why Canadarm? Like, it's an arm. Like, it's really thin and it's just an arm, so it had to be hit somehow. But Craig, first please tell me who came up with this name. I used to think Canadarm is just what Canadians like call their arms. I don't know, but
My Canadarm.
yes, exactly, my Canadarm. And now I know you're from Canada, but I also thought, like, obviously then your eyes are like Canadized. I don't know, but please tell me the truth. Like, did the cool name come first or the actual instrument come first? Like, I even suspect
Probably the instrument. It was probably like might have had some working title when they were working on the project, but then they came up with Canadarm because it's an amalgamation of Canada and arm, and then put it together. And yeah, Canadarm2, I guess, was the second iteration of this arm.
Mm-hmm.
But I don't know who came up with the title, the name. I don't know.
But then are you confirming that they came up with the name first and then thought, oh, it's a cool name, let's build an arm? Like, because I totally suspect that it's a chicken and egg problem. It will never be solved. Actually, the chicken and egg problem has been solved, but I don't want to push a solution on you. But yeah, please.
This has gotten very philosophical. I don't know. Probably the arm came first.
Okay. If you decide to go back to Canada, please let me know from there.
Sure.
Okay. Finally, on Earth, but not about Earth, we announce the annular solar eclipse of this month. So in about a week or so, there is supposed to be an annular solar eclipse going through somewhere around the North Pole. I hope everybody knows what an annular solar eclipse is. You can see in the picture, it's when the moon comes in front of the sun, but the sun is like, oh, you couldn't hide all of me because I'm bigger than you. And then, the sun is still visible as a ring, but there's no experience of complete totality. So the sun is not completely hidden. That does not mean you can still look at it. Please don't look at it at all. But yeah, otherwise it's pretty exciting. It's well, if you happen to take your regular vacation to Greenland, North Canada, or the North Pole, like every summer you guys do, please don't forget to catch this amazing phenomena. Over to you, Roya.
Can we see that from a bowl of water also, or it's also harmful for the eyes?
This is interesting because we don't really mostly, I mean, nobody tells us in the beginning when we are born and we discover that there's something like eclipses, and they all tell us to like, oh, please don't. But we have to understand why this is happening, right? When we look at a blocked sun, our eyes are getting the information that there is less light. So our eyes basically dilate, and that means there is more light coming into the eyes than normal, and of course it's sunlight, so it's even more dangerous. So the extra light that you're getting because of the dilation of the eyes is going to burn your eyes absolutely. As for whether we can look at them on water or through some other medium that is not a special lens that you can wear on your eyes, I'm not sure. Please don't try that. Please don't try looking at the sun anyway, because it's very harmful. But yeah, so this long answer was to tell you that I cannot answer your question right now.
Yeah. So it's better maybe that we search before we do this, because it can be very harmful for our eyes. Because I guess because of the less amount of light, the aperture of our eyes would be even opener than the normal, like when the light is very much, and that will make a lot of problem.
That's right.
I think the safest way to observe an eclipse would be to project the image on some surface, like using a pinhole camera or some simple do-it-yourself projects. So yeah, you can observe. That could be the safest option.
Okay, so are we done? I guess so, yeah, Parit. It was
Well, sadly, yes.
yeah. Yeah, today we get longer than 1 hour, but yeah, because we had a very nice talk by Veena, very fruitful discussion, and now with solar eclipse, we do have something to see in the next coming days, let's say kind of homework for us to the next event, and then we can share our experiences together. So that's it, and thank you for staying to the very last minutes, and see you next month. Bye.
Bye.